Well, now that we have you, let me go ahead and introduce you, Scott.
Okay, thanks, Jack.
Quickly before your phone goes off again.
Exactly.
Scott's currently the program officer at ONR for the Arctic and Global Prediction program. He comes to that program with lots of experience in doing ocean atmosphere models. And I was surprised, Scott, when I read your profile. I think you're Arctic only, but it's bigger than that these days. You're still working on models in other parts of the world as well. So Scott's going to give us a presentation about some things going on in the program, specifically looking at some recent results from the marginal and SeaState research initiatives that he's overseeing. So Scott, welcome.
Okay, thanks, Jackie. Thanks, Olivia. So I'm going to be flying blind here because in the Navy, we have something called the NMCI system, Navy and Marine Corps Internet, although I'm assured that NMCI actually means no more computer interface. So I don't actually see anything from Zoom, and I was getting constant errors. So I did provide a presentation, and so if they can control it, if people can let me know if it's actually working, I'll just step through it.
Yep.
So can folks see my title slide?
Yes, we can see your title slide.
So just let me know when you want to change, and I'll do that for you.
Okay, absolutely. Thanks very much. Okay, so I'm going to talk about a couple initiatives that observational initiatives, but also with modeling and remote sensing efforts that we have going on to look at sea ice in particular, and I'll give you some context and then give you kind of a quick overview and then some of the initial results from these two initiatives. So next slide. So ONR used to have a lot of work going on in high latitude dynamics, pretty large program. We undertook a lot of field experiments and different studies. All of that went away with the end of the Cold War, but about 5 or 6 years ago, we rejuvenated the program in response to the Navy's interest in potentially having to operate in the Arctic and their lack of knowledge about what the environment actually looked like. And so we reinstituted a program. It's called the Arctic and Global Prediction Program, with a nod towards the fact that external factors impact the Arctic, and things that happen in the Arctic actually also impact the mid-latitudes as well. And so it's really a component of a global system. And so it's not just the Arctic research program, but it's Arctic and global prediction. But with respect to the Arctic, our objectives are really to really understand what's happening up there, the physics and dynamics of the emerging environment with the reduction of sea ice, which is really the initial reason that the U.S. Navy was interested in this region, was the fact that they might have to go up there and operate because of increased vessel traffic and activities, and they wanted to have better understanding of what was going on up there. And so, you know, from the physical perspective, we want to understand the reduced ice cover during the summer months, the fact that sea ice is thinner and more dynamic, and then understand the ocean and the atmosphere as well. That's going to require better observing capabilities, new observing platforms, better sensors, algorithm development for remote sensing, and all of that will be wrapped into improving our predictive capabilities in the Arctic environment, building better models, assimilating data from all of these new observations, and then doing a better job of predicting what's going on sort of days to weeks. We're not really thinking about climate change in 10 years from now, but you know, something out to 6 months or a year, lead time predictions would be of interest to us, which is why we're a co-supporter of the SIPN CS Prediction Network, and we're interested in sort of, you know, what might you be able to tell 6 months ahead of time in terms of how the sea ice in particular is going to evolve. So next slide, please. So on the next slide, if it's popping up, is sea ice trends north of Alaska. This is provided courtesy of Sharon Stemerjon from University of Colorado. And it's just showing the trend in spring retreat when the ice melts out. On the left panel, the center panel shows the trend in the autumn advance in ice, which is delayed. The refreeze is being delayed. And so the trend in ice season where there's a lot more open water, and you can see based on the color, the trend is going up, and then the bar graph or the line graph down below shows that you get something like 3 additional months of open water north of Alaska in this area, and this is the area where most of our studies have been taking place, sort of north of Barrow in the Beaufort Gyre region, and so this opening of the the sea ice is something that is critical for understanding the operational environment, for being able to predict the environment. Sea ice is a strong controller of heat flux and momentum flux between the ocean and the atmosphere. And so we really wanted to get a handle on what was going on with the ice. So if you go to the next slide, you should see a timeline of sort of some major ONR Arctic efforts. So we've got a core program that's, persists. That's the top line. But then the very first thing we undertook was something called the Marginal Ice Zone DRI. DRI is Department Research Initiative. It's a focused 5-year effort with multiple investigators to look at some particular problem or some science issue. And so often it's observationalists, theorists, and modelers or remote sensing folks as well, all kind of working together to attack a particular problem. So the first thing we did was Marginal Ice Zone. The second issue, we were looking at SeaState, boundary layer physics. The second one, our acoustics group is undertaking something called Canopy, which I won't get into. And we have a new effort called Stratified Ocean Dynamics in the Arctic. That's another DRI that the field program hasn't happened yet. One slide at the end, I'll mention what that DRI is up to, and then we're really working more on the technology needed to build Arctic mobile observing systems to improve the platforms up there taking data. So this I'm going to briefly cover. Of course, these are huge programs that have lots of different 20-some investigators and each of them involved. But I'm just going to get a touch on the first two of these: the Marginal Ice Zone DRI, for which the field work was done in 2014, and the Waves and SeaState DRI, for which the field work was done in 2015. So go to the next slide. So this just shows the myriad processes that are involved in the Arctic, and the fact that with the open water, you've got a solar insolation reaching the upper ocean, you've got waves and swell, you've got increased fetch, and so you might have to bring the dynamics into play when you're trying to understand what's going on in the Arctic and understand the retreat of sea ice, and as it turns out, also the refreeze of ice in the coming fall. So there's a lot going on. There's a lot of different things, a lot of different feedback processes that have to be accounted for. Okay, so if you go to the next slide, you can see what were the original Marginal Ice Zone DRI goals. So when all the scientists got together, we asked them to define their objectives. So we have scientific objectives and technical objectives. We want to understand the physics that control the ice breakup, characterize the changes in the physics that are associated with this decrease of ice and the increasing open water, and then explore feedbacks that might be at play now and particularly in the future that we need to capture for the models. And then it's sort of on the technical side, the hardware side is we wanted to do this relatively autonomously rather than have ship up there multiple times per year, be able to go up, put a bunch of sensors in place, leave them there as the pack ice devolved into a marginal ice zone and then to open water, and then collect data through that whole period. At the same time, we had a lot of remote sensing involved, trying to image the ice, understand what was going on, sort of from a plan perspective of the sea ice around these in situ instrument networks, so that we could kind of get a more comprehensive picture about how things were actually melting out and how the marginal ice zone is being created and evolving during the year. Okay, so next slide. Okay, let me just do a check. Can everyone can everyone still hear me?
Yes, we can hear you still.
Okay, yes. Good. I was afraid I was just talking to a deadline. Okay, so this is just the Marginal Ice Zone DRI team. You can see it's a cast of a couple dozen top-notch PIs. These guys are all very good at what they do. We've got a whole host of instrumentation, some modeling, some remote sensing. We also had external collaborations with NASA, NOAA, ESA folks. Jackie was involved as well on behalf of the NASA and ESA connection and Ice Bridge. So these are the people who did the actual work, and I've just stolen liberally from them for some background slides and some of their initial results in any case. So if you go to the next slide, this is the experiment overview. So in the upper left of this slide, what you'll see is an array that's laid out, and the idea being that there would be multiple sensors in place existing over sort of a 400-kilometer long strip that would go out in March, be put in the ice, operating from aircraft and helicopters to put this array in place in March, and then everyone would come out of the field. You know, it would only take about a week to put all this stuff in place. And then March, April, May, June, this would just drift with the ice, collecting data. And then the idea was going to be, a north-south array. And as the marginal ice zone kind of behaved normally and marched its way from south to north as it got warmer, we would have multiple looks at this marginal ice zone being created and melting out. Associated with this in situ array, then we were going to take some smaller vessels out, put wave gliders, some swift buoys, and some sea gliders under the ice that would go out under the ice and collect information about the ocean stratification and basal melt and things of that nature. Try to understand, you know, both the stratification in the ocean in open waters as well as in the marginal ice zone and then under the pack ice. Okay, so next slide should be, I have a nice animation of this, but that clearly wasn't going to work. So these are some snapshots. So starting in the upper left, you get the array as it was initially put into the ice. They worked out of Sachs Harbor, flew out, put all these arrays in, including an acoustic navigation array for the sea glider so that they could actually operate under the ice. And then the idea was then to follow this over the year. So you can see progressing to the upper right, 6 weeks later, middle of May, things have translated a bit to the west, but you also start to see some rotation. That increased in May and June. And so by the end of June on the bottom left, what was supposed to be a north-south array was actually an east-west array. And so what we really saw was that the sea ice was moving, you know, faster than we'd done some hindcasts with models trying to understand where we should put the initial array so that you know, in March, so that in July, August, and September, it would be in a location where we could go out with the ships and actually do an intensive observing period and collect additional data. Nothing had it moving or translating or rotating quite this much. And so that was the first surprise, is it's very thin dynamic ice cover and it's doing new things. And so the ice moved more quickly than expected and also rotated. And so we had this array coming out, and then you can see in the bottom right, you know, sort of what it looked like as the ice continued to deplete. The background of all these slides is a blue to white graph showing open waters in blue and completely ice covered is in white. And so by the middle of September 2014, you can see a lot of the sensors were actually in open water, although there were still a few things. The pack ice, the yellow triangles, all the different colors are different platforms. The yellow triangles are actually the sea gliders that were out there under the ice collecting data in the middle of September from a different cruise. Okay, so next slide. Again, this is just some evolution, but what's showing across the bottom, it's the different clusters of sensors at the top. So you can see, again, it was a west to east array by the time we got to middle of August. But across the bottom, you can see what we had was remote sensing images that were being collected that were targeting the actual array locations. And so, you know, for each individual array, we have this time series of remote sensing imagery, high resolution, synthetic aperture radars, as well as other data collected over the array location as it sort of marches through the evolution of the sea ice. Okay, so I'll be skipping ahead. And then I'll be skipping lots of very great observations and work by the PIs, just to pick a few highlights of things. This is an ice mass balance buoy on this next slide. This is slide 11 now. And these ice mass balance buoys are instrumented through the ice with very high resolution temperature strings. You can see the graph on the lower left. It's the depth in centimeters, you know, from sort of the open ocean, which is down below, you know, 150 centimeters in this particular ice flow, and air temperature above. And so you can actually see the temperature of the ice in this case. This is, you know, roughly just over 1.5 meters of ice, and so you can see how it evolves through the year. And then from this particular picture, what you see of note is a melt pond being formed at the surface towards the end of June, and then draining. And so you see this warm water draining through the ice and showing up at the base of the ice that exists throughout July, probably enhancing the basal melt of the ice flow. which I'll get to some of the conclusions here in a second. So you go to the next slide. This was
Scott, you still there?
I think he muted inadvertently.
I'm currently trying to unmute him. It does show him on mute. I don't know what's going on with his system. It won't allow me to unmute him. Meredith, would you mind trying to unmute him? Maybe it's...
Yeah, I just tried and it's not working either.
Okay, Scott, you can try unmuting yourself. The button is in the bottom left corner of your screen. You have to scroll over it to see the mute button. Okay, it looks like he's off mute. Yep, there you go.
okay. You guys can hear me?
Yeah, we can hear you now.
Okay. Yeah, I have some error that keeps popping up and then it bombs out of the program. So yeah, so anyway, this was a common result, which is where the basal melt was actually stronger than the surface melt in most of the ice mass balance buoy locations. So let me just accelerate a little bit and go to the next slide, which is some of the resultant comments. And so what we expected to see was, you know, with this open water, we thought maybe that we would see waves and swell coming in, breaking up the ice. You know, part of the 2012 ice minimum was caused by, you know, storms that came through, and the waviness actually accelerated the ice loss. And we thought maybe that we'd watch some of that. So there were a lot of wave buoys, you know, in these clusters of sensors, and we were going to, you know, watch how the dynamics actually broke things up. And what we ended up seeing in 2014 anyway was it was largely a thermodynamic melt, and so it was warmer water below and warm surface conditions that just sort of melted the ice, and it created fields of rotten ice where it was, you know, it was very we were sort of joking that it was a marginal ice zone because the ice was very marginal. It wasn't very strong ice, and so we didn't see a lot of wave action until the ice actually broke up, and that was sort of ubiquitous across all the different clusters. There was a lot of oceanic variability in the marginal ice zone, so I won't talk about it, but there are a lot of other observations of the upper ocean and interesting things about the fronts and the solar insulation heating the water, and the difference between the stratification under the ice and outside the ice that we saw with the sea gliders. But so the general tenor, and there's a lot going on here. There is a special issue of an Elementa coming up with a lot of the initial findings from this group. But you know, the ice is thin and fast. It's a, you know, sort of rotten ice field. It thermodynamically melted. But we have all these observations. We're trying to put it all together and really understand what's going on in the marginal ice zone at that time. So let me quick. I think this is going on a bit, and then who knows when the program's going to crash again. But if we go to the next slide, I can give a quick overview of the SeaState and boundary layer physics DRI. Where this was not sort of the autonomous array that we had previously. We were going out in this Kuliak later in the year to really study the freeze up, to really understand how the sea ice controls or damps waves and swell, what waves and swell do to the refreeze of the ice. And so again, a cast of a couple dozen PIs. You can see that on the bottom right, the SeaState and boundary layer physics of the emerging Arctic Ocean science plan that they put together. And on the left is a pretty picture of all the different sensors we had out there. And in this, okay, you can go to the next slide, but I'll just sort of mention lots of observations, different groups taking them. So you can hop to the next slide, and you can actually see the cruise track of the Kuliak. And so this was a pretty late cruise. So rather than being out there in August and September, they left in September, and they were out there all of October, kind of watching the refreeze, just, studying what was going on. They were out there as the ice progressed to the south in the refreeze period, and so they had ice stations. There was a tongue of multi-year ice that still was hanging around there, sort of at the shelf break. all along the northern slope of Alaska. And so there was ice there, and that became an important precursor to the refreeze sort of later on in the year. But then they broke their way out, and they were in open water for a while, and they saw various conditions. And so this was really a study. They had a lot of different synoptic conditions that they were looking at. You know, winds on the ice, winds off the ice, waves and swell. And so if you go to the next slide, one of the big stories was pancake ice, which is typically a huge feature in the Southern Ocean, but not so much in the Arctic usually. But with a lot of the open water and the fetch and the waves and swell, they observed quite a bit of pancake ice, and it was an important part of the refreeze and the redevelopment of the ice cover in the fall months. So if you go to the next slide, just some pictures of the various ice conditions that we're seeing. This is from Ben Holt at JPL. These were all taken over a period of a few days during one of these synoptic events where they saw some things. And so if you go to the next slide then, which just sort of says synoptic conditions are important, there was a period in, and this is just to show, there was a period when the waves or the winds were on ice. So they were over the ocean. Winds were from between October 11th and October 12th. They were from the southeast. And so the interesting thing from those two images on the left, from October 11th to October 12th, was the reduction in ice cover. Actually, even though you see a lot of things go to bright yellow, which is more ice, in the area where the red oval is where the ship was. And so they were sitting in a lot of ice. And with these winds and waves and swell, what ended up happening is there was a mixing of the upper ocean. So the near surface temperature maximum from the solar insolation that was there in August and September, the waves and swell actually mixed that upward, melted all the pancake ice they saw, and they were back in open water again. And so they saw a lot of these sort of synoptic events. And then, a week later, they were in another place where the wind was off the ice. So it was from the north coming to the south. And so then what they saw was, a very quick refreeze as the colder winds came off, and there was a huge heat flux out of the ocean. And so from the 17th to 19th there, you see, a lot of ice formation as you get the winds off the ice. And so this just means that there's a lot of, really sub-mesoscale and small scale situations going on in terms of the refreeze. And so trying to understand how all these things, play into it is actually quite important. So let's just hop to one of the summary slides, SeaState DRI results and comments. They have a special issue coming up in JGR Oceans with their initial findings. Preconditioning matters. There was this ice tongue. The fact that there was some multi-year ice hanging around actually had played a big role in ultimately what happened in terms of the heat flux out of the ocean and the refreeze. Near surface temperature maximum mattered, and in fact that there was this ready source of heat that could be mixed up that could prevent the refreeze and sort of delay the onset of refreeze. Wave ice feedbacks are important in terms of the pancake formation, attenuation of waves and ice. Again, on ice winds, you get pancakes and mixing. Off ice winds, you get nihilist ice and rapid freezing. There was ice edge loitering near the shelf break when you did have this warmer water coming up. So again, there are a lot of feedbacks that have positive and negative signs, and you have to. It's a very complex situation in terms of trying to do a heat budget, trying to figure out, which actual process is important and when they're important. But they did observe larger and longer waves and swell, pancake ice, and the vertical mixing of heat. They did go and study, what was one of the more primary reasons they were going out and doing this was looking at the sea ice and looking at how that attenuates surface turbulence and wave activities. And so they looked at waves outside the marginal ice zone and how it propagated into the field. And of course, there's a lot of high frequency scattering and attenuation so that you really see the longer waves propagating farther into the ice. And so that was used to develop new source and sink terms for the WaveWatch 3 wave model. And so those are going to be available in terms of being able to do a better job of predicting the surface conditions and the waves in the Arctic or in the presence of any ice. So Eric Rogers at Naval Research Laboratory is working with the WaveWatch 3 folks to get all those new observations in there. And then this pancake ice really, these new processes and ice formation create a rougher first year ice field. So it's not just all nihilist ice that forms a nice smooth first year ice field. You get a lot of ice rafting and it's a rougher ice field. I don't know necessarily what it does to the strength of the ice itself, but it's definitely a different process than it's sort of been operating previously. So we go to the next slide, just a little preview. We're doing something called stratified ocean dynamics in the Arctic DRI. That'll have a field effort next summer, where we'll go out and again do gliders under the ice, really looking at surface stratification and near inertial waves, and again, sort of atmospheric forcing on the open ocean, try to figure out what's going on. But there will be certainly ice covered and non-ice covered periods, and we'll have again multiple sensors kind of in the ice. So it's a little riff off of the marginal ice zone study and the SeaState study, but really looking more at processes in the upper ocean in that case. So hopefully I've not been dropped offline again. So that was just a very quick run through that. I'm happy to take any questions with the caveat that I just send money out and all the smart people actually do the work, and I think only a few of them are online. Thanks.
Thanks very much, Scott. Sorry for all the technical challenges, but I think you did a great job of providing a good summary of what's going on in those programs and what's coming up. Any questions from folks? Scott, can you, how, as far as technology development, you mentioned that was another key goal of both of these DRIs and some upcoming ones. Can you just give us a little sense of what you've seen technologically that you feel has really, modified how we're making observations, or what we, or maybe some gaps that it's revealed?
Well, I mean, I think, can everyone hear me? I just had a little screen pop up that said something. Okay, good. Yeah, so I think, autonomy and persistence are definitely key factors, and things like the International Arctic Buoy Program are very useful, but that's a limited number of observations that are taken from, from those platforms. And so I think sort of expanding the capabilities that we have, you have things like the ice tethered profiler and ice mass balance buoys. These are all great, but we need to get them, they're all just sort of point measurements. We get, fortunately they move with the ice, and so you sweep through the ocean, you sweep through the Arctic with these measurements. But I think where we want to go at ONR is we want to develop the capability to do mobile observing. So you can go out and put a sensor suite out there with more capability, be able to touch more of the ice, fly over more of the ice, fly under more of the ice, collect more data than you get from just the point measurement. So we're trying to work towards that with something called Arctic Mobile Observing System to try to advance the capabilities under the ice, in particular navigation. We have, I think, an ability to acoustically navigate under the ice now. And so using floats, using gliders, using other platforms under the ice that don't need to get to the surface now to get their GPS fix, but they can actually, use the acoustic signals to navigate is important. And I think we need to continue doing that so that we can really get more of a pan-Arctic view about what's going on. These are sort of some examples from the Beaufort Gyre, but they're one-offs. 1 year. Develop the capability. I think we need to really work towards more, towards an Arctic observing system, both, interagency in the U.S. and internationally, to try and get, all these things fleshed out. But I think there's still some technology development that needs to take place to do that. In terms of actual improving predictions, I think one of the issues is we want to get this data out in real time. And so, real-time reporting of what's going on in terms of the, ocean stratification, for example, or ocean velocities would be very useful. So we've got to work on sort of two-way communications under the ice, so that as you have sensors out there that are collecting data, if you're picked in the ice like ice mass balance buoy or ITP, you can get that data back out. If you're flowing under the ocean, you're either looking upward at the ice or you're taking stratification information not right at the ITP location. You have valuable data, but how do you get it out? So we want to be able to do that two-way acoustic or optical communication. get that back through satellite so that you can actually assimilate that into models and try and predict what's going on. So I think we've got many of the tools. I think there's still some things we have to develop, but really it's the persistence and the number of observations that are out there. They're just often not sufficient for for doing what needs to be done. And so I think we have to distribute these things out and get ways to deploy them and for them to exist for months, but preferably multiple months into years once you get them out there, because it's awfully expensive to go up there. And so the longer we can get these platforms and sensors to persist, the better off we'll be in terms of having observations.
Great, that's very useful. Thanks. Any other questions for Scott?
Yeah, Scott, this is Renee Tetusco, National Weather Service, Alaska Region. Can you hear me?
I can. Thank you, Renee.
Hi, Scott. Thanks very much for this presentation. As you know, I presented this particular slide at a Europe Polar Prediction meeting last September, I think it was, in the UK. And the YOP itself has officially begun its 2-year field campaign. If you're a member of the polarprediction.net mail list, you probably saw the announcement that came out from the International Coordination Office. I'm just wondering whether or not you've had any additional, perhaps has anybody from the International Coordination Office reached out to you regarding the observations, in particular the special observation periods in both 2018 and 19?
I have asked the SOTA DRI team to officially register and be a sanctioned program by PPP and YOP. I don't know if they've done that yet, but we certainly plan to provide as much data in real time as possible for 4-year polar prediction and for the Polar Prediction Project as well.
Great, and I appreciate the comment. I was going to ask you about the data being made available in real time, but that sounds like that's something you're working on.
Yes, some of the data is available, and some of it is not, because it's got to be processed, and everyone's got to polish their rock before they show it to anybody else for some of the stuff. But some of the other data is for example, things like ITPs are routinely made available in real time, and that's very useful to folks who want to in situ look about what's actually happening in the Arctic. And so yeah, to whatever degree possible, I've asked them to make that available in real time, and they will be a part of the YOP data.
Excellent.